A world map from 1513 shows Antarctica without its ice. This single, impossible detail is just the beginning of a global historical mystery. Ancient maps exist that chart coastlines with a precision that defies the technology of their time, depicting lands that should have been completely unknown to their creators. By the end of this journey, you will possess a new framework for human history, one where the timeline of exploration is far more fluid and fascinating than any textbook suggests. We will examine charts drawn on gazelle skin that hold frozen secrets and medieval sailing manuals that rival modern GPS in their accuracy. How did mapmakers centuries ago record geographical truths we have only just confirmed with satellites? What does this suggest about the forgotten voyages and perhaps even the lost civilizations that came before us? Are we prepared to accept that the past might be far more advanced and far more mysterious than we have ever dared to believe? Picture the scene in a quiet study centuries ago. A scholar carefully unrolls a large chart made of treated animal skin, its edges worn from travel. His candle flickers as his gaze traces the coastlines and his breath catches. There, drawn with confident lines, is a continent. It is a land his own world believes is nothing but a frozen, mythical void at the bottom of the globe, a place of monsters and endless ice. Yet on this vellum, it is not a blank space filled with sea serpents. It is a detailed coastline, complete with bays, inlets, and mountain ranges where no mountains should be known. This is the moment of encountering a cartographic anomaly, a map that holds knowledge it simply should not possess. To understand why this is so shocking, we must first grasp what accurate meant before satellites. For most of human history, mapping a coastline was a painstaking, dangerous, and deeply flawed art. Sailors in wooden ships used simple tools to measure the angle of the sun or stars, estimating their position with errors that could span hundreds of miles. They sketched what they saw from the deck, a view that revealed only a sliver of land at a time. The result was often a distorted puzzle piece, a coastline that might be recognizable in its general shape, but was riddled with mistakes, capes in the wrong place, islands missing, entire gulfs drawn too wide or too narrow. An accurate pre-modern map was one that got the general shape roughly right, allowing another sailor to navigate from one major port to another without getting hopelessly lost. It was not a precise, scaled blueprint of the land. This is what makes the anomalous maps so utterly bewildering. They do not display the kind of errors you would expect from guesswork or hearsay. Instead, they show a different class of information entirely. Historians who study these puzzles, like Professor Charles Hapgood, point to several telltale signs. First is longitudinal accuracy, placing landmasses correctly east to west on the globe, a feat that was scientifically impossible until the 18th century with the invention of precise maritime clocks. Second is the inclusion of specific, subtle topographic features, the exact curl of a river delta, the particular shape of a hidden bay, a chain of small offshore islands. These are details you only get from being there, from meticulously surveying the land, not from a sailor's story told in a tavern. The most profound anomaly, of course, is the depiction of land under ice. The map from 1513 shows the continent we call Antarctica, but it shows its coastline free of the ice sheet that has buried it for millions of years. This is not a case of guessing there might be land down there. It is a case of drawing the literal bedrock coastline, the shape of the continent itself, which has been hidden under more than a mile of ice for epochs longer than humanity has existed. How could a Renaissance cartographer have accessed that knowledge? The map presents us with a stark choice. Either it is a spectacular, meaningless coincidence, a lucky set of ink strokes that just happen to match what our satellites now see, or it is a copy of a copy of a copy of a much, much older source map drawn by someone who saw that land when it was last ice-free. If these are forgeries or fantasies, why do their greatest mistakes so often turn out to be hidden geographical truths? The answer to that question lies in our first specific example, a chart that redefines the story of exploration. In the summer of 1929, within the hushed archives of Istanbul's Topkapi Palace, a curator made a discovery that would ignite a century of debate. He was sorting through a stack of neglected documents when his hands carefully unrolled a large, aging chart drawn on gazelle skin. At the bottom was a signature, Piri Reis, an Ottoman admiral and cartographer, and a date 1513. This was not just another old map, it was a fragment of a lost worldview, and it contained geographical secrets that should have been impossible for its time. The Piri Reis map shows the Atlantic coasts with a familiar, though imperfect, medieval style. But as the eye moves south and west, the details become astonishing. The eastern coast of South America is rendered with a startling clarity, and below it, connected by a curious land bridge, lies a landmass that many researchers believe represents the northern tip of Antarctica. Specifically, the coastline corresponds to an area known as Queen Maud Land. The shocking part is not that Antarctica is there, it is the shape of its coast. This coastline has been entombed under a colossal ice sheet for at least 12 million years, a depth of ice that modern radar and sonar have only recently penetrated to reveal the bedrock below. Yet the Piri Reis outline shows a striking, some argue uncanny, resemblance to that hidden subglacial topography. How could a 16th century admiral, relying on the reports of sailors who never ventured that far south, possibly chart a coastline buried under millennia of ice? The map itself offers tantalizing clues in its own margin notes. Piri Reis was remarkably candid about his sources. He wrote that he compiled his work from about 20 older charts and mapi mundi, including Portuguese maps captured in battle, and most intriguingly, charts dating back to the time of Alexander the Great. He was not claiming to have discovered these lands himself. He was a compiler, a scholar piecing together a world picture from sources he considered authoritative, some of which were already ancient in his own day. The anomalies on the map are precise and puzzling. The Andes Mountains are depicted running parallel to the coast, a correct geographical relationship that European explorers of the era were barely beginning to understand. The map shows a land connection between South America and the Antarctic Peninsula, which we now know does not exist, but some analysts suggest this could be a misinterpretation of the very narrow Drake Passage, or perhaps a copyist's error from a much older source that showed the continents in a different configuration. Alongside these accurate features are drawings of ships and mythical beasts, a common practice of the time to fill blank spaces with both decoration and legend. This mix of the precise and the fantastical is what makes the map so compelling. It is not a perfect, sterile satellite image. It is a human document layered with knowledge, error, and artistry. To grasp the scale of the mystery, consider a modern comparison. When researchers overlay the Piri Reis depiction of the Antarctic coastline with sonar maps of the continent's bedrock, the correlation in certain areas is difficult to dismiss as pure chance. The capes, the bays, the general profile, they align in a way that suggests more than a lucky guess. It suggests measurement. This forces a profound question. If Piri Reis was working from source maps that were themselves copies of ancient originals, what civilization, in a time before recorded history, possessed the knowledge and the means to survey a continent that would later vanish under the ice? The map fragment from Istanbul is not an answer but a gateway, pointing us toward a shadowy prehistory of exploration that our textbooks have yet to acknowledge. The Piri Reis map is a fragment, but it points to a tradition. That tradition finds its purest, most perplexing expression not on gazelle skin, but on vellum, in a family of maps that revolutionized navigation. They are called Portolan charts. Imagine a sea captain in the 1300s, his hands tracing a dense web of lines radiating from compass roses across a detailed coastline. This was not a decorative showpiece for a noble's library. It was a working tool, a functional diagram for survival at sea. Unlike the symbolic world maps of the era, filled with religious imagery and mythical lands, Portolan charts were ruthlessly practical. They depicted one thing with breathtaking focus: the coastlines of the Mediterranean and Black Seas. Their accuracy is not just impressive for the time. It is startling. The shape of Italy's boot, the intricate curl of the Greek islands, the precise distance from Barcelona to Tunis. These charts rendered them with a consistency and correctness that would not be surpassed for centuries. Scholar Tony Campbell highlights the central mystery of these charts. They appear in the historical record, almost fully formed around the late 13th century. There are no clumsy, experimental predecessors showing a gradual improvement. It is as if this advanced cartographic technology simply arrived. The secret to their utility lies in the web of lines called Rhumb lines or loxodromes. These lines radiate from multiple compass roses drawn across the chart. A sailor could draw a line from his starting point to his destination, and then follow the constant compass bearing indicated by that line's angle. This created a navigational grid that turned the open sea into a manageable, if still dangerous, puzzle. But the grid is only useful if the coastline it connects is drawn correctly. And here, the precision is stunning. Take the Adriatic Sea, for instance. A Portolan chart from 1350 will show its long, narrow body, the indentations of major ports like Venice and Ragusa, and the profile of the Italian and Balkan coasts with a fidelity that feels modern. The Aegean archipelago, a chaotic scatter of islands, is rendered with an understanding of relative positions and shapes that suggests direct, meticulous surveying. Let us follow a hypothetical voyage. A Genoese merchant captain in 1380 plots a course to Alexandria. He lays his ruler on the chart from his home port, aligns it with the Rhumb line pointing southeast, and reads off the compass bearing. As he sails, the chart tells him what headland to expect next, how far it is to the next safe harbor, and the orientation of every bay and river mouth along the North African coast. This was not guesswork, it was geometry applied to the real world. The enduring question is how the original surveys were done. To achieve this level of consistency across hundreds of charts made by different hands over 2 centuries, they must have all been copying from a set of extraordinarily accurate master charts. But who created those masters, and with what methods? The coastline had to be measured headland by headland, bay by bay, with an understanding of true distance and bearing that seems to leap ahead of other contemporary sciences. It implies a coordinated, large-scale effort of coastal mapping, a project whose records have vanished from history. The Portolan charts work too well to be a happy accident. They are the silent, durable evidence of a lost school of practical geography, a system so effective that sailors relied on its logic for generations, never quite knowing how their most precious tool had first been drawn. Decades after the Piri Reis map was drawn, another cartographic puzzle emerged from a family's attic, wrapped in layers of legend and accusation. In 1558, a Venetian nobleman named Niccolò Zeno published a map and a narrative that ignited immediate controversy. He claimed it was based on the secret voyages of his ancestors, the Zeno brothers, who had sailed into the North Atlantic in the 1390s. The Zeno map is an enigma, a detailed chart of the northern seas that shows real geography intertwined with lands that simply do not exist. It depicts the Scandinavian coastline and a remarkably accurate outline of Greenland, labeled in Groenland, with a shape that European cartographers would not consistently match for another 200 years. Yet alongside these real places, the map is populated with phantom islands, Friesland, a large island south of Iceland, appears repeatedly on maps for centuries, searched for by explorers who never found it. Icaria and others dot the sea, alongside a mysterious western landmass labeled Estatiland. The debate among historians is fierce. Some dismiss the entire work as an elaborate 16th century hoax, a fabrication by Niccolo Zeno to bring glory to his family name. Others, however, hear a faint echo of truth in the chaos. They propose the map is not a pure invention, but a badly corrupted copy of much older, genuine charts. These source charts, the theory goes, could have been based on the real navigational knowledge of Norse settlers in Greenland and Vinland, or perhaps on the logs of forgotten Portuguese expeditions that ventured west before Columbus. This idea transforms the map from a simple forgery into a palimpsest, a document where real data has been obscured by time and poor copying. Take the case of Estatiland. Many researchers see in this name and its placement a distorted reference to the North American coastline, possibly Newfoundland or Labrador. The Norse had established a short-lived settlement at Elance Aux Meadows in Newfoundland around the year 1000. A fact confirmed by modern archaeology, but largely absent from mainstream European cartography for centuries. Could local Norse sailing knowledge, passed down or recorded in now lost charts, have filtered back to Europe and eventually into the hands of a mapmaker like Zeno? The accurate Greenland is the strongest clue. Its detailed, jagged eastern coastline on the Zeno map is too correct to be a lucky guess. It suggests a source that came from someone who had actually sailed along its fjords. The Phantom Islands, then, might be a tragic case of cartographic telephone. A real island, perhaps the Shetlands or the Faroes, gets mislabeled in one copy. That mislabeled island is then drawn in the wrong place in the next copy. Over decades of reproduction, a single geographical truth can splinter into multiple phantom duplicates, confusing generations of sailors. The Zeno map embodies this process. It is not necessarily a lie, but a story that has been told and retold until the original facts are buried under layers of misinterpretation. This raises a haunting possibility. What if other ancient maps we dismiss as fantasy are not inventions, but simply the end result of this same process of corruption? What if their core truth is still there, waiting to be separated from the noise of centuries? The journey to find that original source leads us to a single, extraordinary book that claims to be a copy of the world's oldest map. These maps, then, are not isolated riddles but pieces of a single, larger question. What source could possibly explain their impossible knowledge? To answer that, we must confront a fundamental assumption about human history itself. Our standard narrative is one of linear progress, a steady climb from simple tools to complex technology. But what if the path is not a straight line? What if it is more like a series of waves with peaks of advanced understanding that rose in deep antiquity, only to recede and be forgotten, leaving behind only the faintest traces in myths and perhaps in maps? This idea challenges the very framework of our past, and it has given rise to two compelling and often contentious schools of thought. The first is often called the lost civilization hypothesis. Popularized by researchers like Graham Hancock, it proposes that a sophisticated, global maritime culture existed thousands of years before the rise of Egypt or Sumer. This advanced society, possessing knowledge of astronomy, geometry, and seafaring, meticulously mapped the world. Then, according to the theory, a cataclysmic event, perhaps a rapid shift in sea levels or a comet impact, shattered this civilization, scattering its survivors and reducing its grand knowledge to fragments. These survivors would have carried their charts and stories to the emerging cultures of the ancient world, where they became the source material for later mapmakers like Piri Reis. The appeal of this model is its elegant simplicity. It provides a single, unified source for all the anomalous data, a golden age of explorers whose legacy is etched in vellum. The second, more conservative explanation is the theory of accumulated and lost knowledge. This view does not require an unknown super-civilization. Instead, it argues that the ancient world was far more interconnected and its explorers far more capable than our textbooks acknowledge. Known seafaring cultures, from the Minoans and Phoenicians to the Polynesians, undertook voyages of discovery that have simply been lost to the written record. Their practical coastal surveys, passed down through generations of sailors and copied onto perishable materials like papyrus or wax tablets, could have formed a body of geographical knowledge that was later consolidated. Consider the Phoenicians who circumnavigated Africa according to Herodotus, or the Minoans whose palace at Knossos held detailed frescoes of distant shores. Imagine a vast, informal Bronze Age trading network, where a sketch of a strange coastline drawn by a Cretan merchant is traded to a Phoenician captain in Cyprus, who adds his own notes before it eventually finds its way to a library in Alexandria. Over millennia, this accumulated data could have reached a surprising level of accuracy, only to be dispersed and degraded with the fall of successive empires. Many mainstream archaeologists urge caution, however. They point out that an absence of evidence is not evidence of a grand, forgotten age. The historical record is full of gaps, they acknowledge, but we must build theories on what we can verify. As one professor of archaeology notes, it is human nature to romanticize the past, to populate its silences with grand narratives. The truth, they suggest, is often more incremental, more messy, and no less impressive. The strength of the accumulated knowledge model is that it works within the known parameters of human history, relying on the documented prowess of ancient sailors rather than an unproven precursor culture. Yet, both models must contend with the same stubborn evidence. Whether the source was a single lost culture or a patchwork of forgotten voyages, the result is the same: maps that contain seeds of truth their makers should not have possessed. The phantom islands on the Zeno map could be the garbled memories of real Norse landfalls in North America. The Portolan chart's precision suggests a coordinated surveying project whose records have vanished. And the Antarctic coastline on the Piri Reis fragment points to a source so ancient it depicts a world before the ice. The debate between these frameworks is not merely academic, it shapes how we interpret every anomaly. It forces us to ask, what are we more willing to accept, that human history is far longer and more complex than we thought, or that ancient peoples were far more skilled and adventurous than we have credited them for? Before we can choose, we must examine the practicalities. What tools could these ancient surveyors, whether they were Phoenicians or members of a lost culture, have possibly used to achieve such feats of measurement? The answer may lie in a simple, elegant device that translated the vault of heaven into a chart on a table. A single shadow cast by a stick at noon, measured in 2 different cities, gave one man the size of the world. Eratosthenes, the head of the great Library of Alexandria in the 3rd century before the Common Era, performed this feat with elegant simplicity. He knew that on the summer solstice in the city of Finé, the sun shone directly down a deep well, meaning it was directly overhead. On that same day in Alexandria, he measured the angle of a shadow cast by a vertical rod. That angle, about 7 degrees, told him the distance between the 2 cities represented 1/50th of a full circle. Knowing the travel distance between them, he simply multiplied by 50 and arrived at a figure for the Earth's circumference that was within a few percent of the modern value. This was not magic, it was geometry. It proves that ancient thinkers possessed the intellectual framework to understand their world as a measurable sphere. So, if they could measure the planet itself, what about its coastlines? The tools were humble but effective. The gnomon, that simple vertical stick, was a cornerstone. By tracking the length of its shadow at local noon over a year, a scholar could determine his precise latitude, his north-south position on the globe. For sailors, the cross staff and later the astrolabe allowed them to measure the angle of the sun or the North Star above the horizon, giving them their latitude even on a rolling deck. Distance over land could be measured with chains or ropes paced out by trained walkers. The true art, however, lay in combining these tools with relentless observation. Imagine a Phoenician galley captain tasked with charting a new stretch of coast. He would sail close to shore, identifying prominent landmarks, a distinctive mountain peak, a jagged cliff, the mouth of a wide river. From his ship, he would use a simple sighting instrument to take a bearing, noting the angle of that landmark relative to north. He would sail a known distance, perhaps estimated by throwing a log overboard and timing its passage along the ship's length, a method called dead reckoning. Then he would take another bearing on the same landmark. With two angles and an estimated distance, he could use triangulation, a basic geometric principle, to plot the landmark's position relative to his course. Repeating this painstaking process for every bay and headland over countless voyages and generations could slowly build a remarkably accurate coastal outline. This was a collective, cumulative science where each captain's logbook added a few more puzzle pieces to a growing master chart. The limitations, however, were severe, and they highlight why the anomalous maps are so baffling. The greatest hurdle was longitude, determining your precise position east to west. While latitude could be found from the stars, longitude required knowing the exact time difference between your location and a fixed point, like your home port. Without an accurate portable clock, this was nearly impossible at sea. A small error in time could mean an error of hundreds of miles. This is why, for centuries, ships often sailed north or south to their desired latitude first, then turned east or west and simply sailed until they hit land, a risky and inefficient method. Given this technological ceiling, how do we explain maps that show continents in their correct longitudinal relationships? Or, even more perplexing, maps that seem to depict landmasses like Antarctica with a shape that requires knowledge of its true longitudinal extent? The known tools of Eratosthenes and the Phoenician captain are sufficient for local, coastal mapping. They can explain the precision of the Portolan charts in the Mediterranean, a relatively confined sea. But they strain to account for a global picture assembled with such apparent coherence. This forces us to consider a more speculative possibility. Could the ancient master surveyors have used a different kind of clock, one not made of gears and springs, but of the sky itself? Some researchers point to the possibility of using lunar eclipses as global timekeepers. Since a lunar eclipse is visible simultaneously across half the Earth, and ancient astronomers could predict them with great skill, a network of observers from Babylon to Carthage to Giza could, in theory, use such an event to synchronize their local times and calculate longitudinal differences between them. This would be a monumental, coordinated effort, requiring stable institutions and a shared scientific language across continents. There is no direct evidence such a project was ever undertaken, but its theoretical possibility shows that the ancient mind was capable of conceiving solutions we have overlooked. The gap between the simple shadow stick and the complex global map may not be a gap in technology alone, but a gap in our understanding of ancient ambition and collaboration. We are left with a profound disconnect. The tools we know they had could create accurate fragments, yet some maps suggest a synthesis of those fragments into a whole that seems to leap over the longitudinal abyss. This brings us back to the central choice. Was this synthesis the product of a lost, coordinated science, or is it merely an illusion in the parchment, a trick of copying and coincidence? To move closer to an answer, we must look at the one map that claims to be a direct copy of the very first World Survey, a document that takes the mystery to its furthest edge. The library of a 16th century French mathematician held a secret that would lie dormant for centuries. Orontius Phineus was a respected scholar, a man of numbers and celestial mechanics, who published a world map in 1531. At the southern pole of his carefully drawn globe sits a continent. It is not a vague, suggestive shape or a decorative monster. It is a detailed landmass labeled Terra Australis, with a defined coastline featuring indentations that look like gulfs and peninsulas. Most startling of all, the interior is crisscrossed with lines that resemble river systems flowing from central highlands toward the sea. This is a map of Antarctica, but it shows a continent that is green, fertile, and utterly ice-free. The Phineas map presents a direct and elegant challenge. It does not show the icy waste described in later explorer tales. It shows a land that could support rivers, a land that could be mapped from the ground. Decades later, historian Charles Hapgood subjected this map to a rigorous test. He took a transparent overlay of the Phineas coastline and placed it over a modern seismic map of Antarctica's bedrock, the true shape of the continent buried under miles of ice. The correspondences he reported were difficult to dismiss. The overall profile aligned with remarkable fidelity, but the details are what truly captivate. Phineas depicted the southern continent as two large landmasses separated by a substantial body of water running from a central sea up into a deep gulf. On a modern map, this is eerily reminiscent of the Transantarctic mountain range, which divides East and West Antarctica, and the Ross and Weddell Seas which bite deep into the continent on either side of that range. The map shows a prominent peninsula that aligns with the modern Antarctic Peninsula, and a specific coastal bulge that Hapgood identified with the Princess Martha Coast region. These are not random scribbles. They are specific geographic features that would be completely invisible to any human eye from the time of Phineas until the advent of subsurface radar scanning in the 20th century. Skeptics offer alternative explanations, of course. Could it be lucky guesswork? Some argue that Renaissance cartographers, believing in a symmetrical world, simply drew a speculative southern landmass to balance the northern continents. But symmetry would suggest a simple, roundish shape, not a complex coastline with precisely placed estuaries and inland seas. Others suggest Phineas was conflating all the rumors of southern lands from Portuguese and Spanish voyages, stitching together bits of Patagonia, Tierra del Fuego, and maybe even Australia. Yet this theory struggles with the map's internal coherence. The landmass is one unified continent, not a collage of disparate fragments, and its river systems imply a consistent continental-scale hydrology that does not match the geography of those other southern lands. Walking through a specific example makes the case tangible. Look at the area Phineas labels as the Gulf of the Current. On his map, it is a deep inward curve on the continent's edge. On the modern subglacial map, in approximately the same position, we find the vast indentation of the Weddell Sea. The coastline Phineas draws to the east of this gulf, the Princess Martha Coast, follows a curve and a set of projections that align closely with the bedrock contours revealed by science centuries later. The probability that a 16th century scholar, guessing, could land on this specific arrangement of coastal features is astronomically low. The most logical conclusion is also the most profound. The Oronce Phineas map is very likely a copy, filtered through the cartographic styles of his time, of a much older source map. And that source map could only have been drawn during a period when Antarctica's coasts were clear, its rivers flowed, and its mountains were visible to surveyors on the ground. This points to a remote epoch, a time of profound climatic warmth long before recorded history, when someone stood on that now frozen shore, looked inland, and began to chart a world we are only now rediscovering. The implications of the Phineas map pull us into a scale of time that is almost impossible to grasp. We are asked to envision Antarctica not as a continent of eternal ice, but as a landscape of forests, rivers, and temperate shores. This is not a recent thaw, but a vision from deep geological time. The science of paleoclimatology confirms this was once a reality. geologists studying sediment cores and fossil records tell us Antarctica was last largely ice-free during a period called the Eocene Epoch, which ended roughly 34 million years ago. To put that in perspective, this was an era when the ancestors of modern whales were still four-legged creatures walking on land. The timeline is staggering, placing this green continent in an age long before the emergence of any hominid, let alone a civilization capable of transoceanic navigation and precise cartography. Yet, when researchers compare the coastline on maps like that of Oronce Finé to modern sonar maps of the subglacial bedrock, the alignment in key areas is provocative. The shapes correspond more closely to that ancient, buried coastline than to the jagged edge of the modern ice shelves. This presents a paradox of sources. If the maps are based on human observation, who could have been there to see it? This question opens the door to more speculative explanations. One theory, as we have touched on, proposes a lost prehistoric culture of advanced seafarers, a civilization that flourished and mapped the world before a cataclysmic reset erased them from history, leaving only their charts as a legacy. A more fringe idea, often discussed in popular culture, suggests the knowledge came from an external, perhaps even extraterrestrial source, a notion that most academics dismiss due to a complete lack of evidence. To navigate these ideas, we must distinguish between different kinds of ancient climate change. Many people are familiar with the last glacial maximum, the peak of the last ice age, which ended around 11,000 years ago. During that time, massive ice sheets covered much of North America and Europe, and global sea levels were over 300 feet lower than today. This exposed vast continental shelves, creating land bridges like Beringia. Some have wondered if the anomalous maps are simply showing coastlines from this more recent period. However, when examined, this does not fit. The maps do not show the dramatically expanded coastlines or the land bridges that a 300-foot lower sea level would create. They show continents roughly in their modern positions with their familiar profiles. Antarctica, crucially, was still heavily glaciated during this recent ice age, just as it is today. Its bedrock coastline remained hidden. This clarifies the mystery. The maps are not depicting a world from 11,000 years ago. They seem to be depicting a world from tens of millions of years ago, a world for which we have no human history, only geological testimony. The source of this knowledge retreats into a profound and silent past. It means the original survey, if it was a survey, occurred in an epoch so remote that it reshapes our entire perspective on the possibility of human, or perhaps post-human, history. The coastline on the parchment is not just a line, it is a message in a bottle from a different age, and we are left to wonder who or what first placed it in the sea. The Phineas map offers a vision of a green Antarctica, but what if the truth was even stranger? In 1737, the French geographer Philippe Buache presented a very different southern continent. His map is a work of elegant theory, drawn with clean, almost geometric lines. It shows not one landmass but two large circular islands, separated by a wide, frozen sea that stretches from one side of the continent to the other. This was not claimed as an ancient document. Buache was a man of the Enlightenment, and he created this map using a principle called theoretical geography. He believed the Earth's landforms were arranged in symmetrical patterns. Mountain ranges in the north, he reasoned, would have their counterparts in the south. He looked at the known landmasses and projected where their mirror images should be, using logic and geometry to fill in the blank spaces at the bottom of the world. His Antarctica was a beautiful hypothesis, a cartographic thought experiment rendered in ink. Yet when we look at this speculative drawing today, a shiver of recognition runs through it. The most striking feature, that central sea dividing the continent into two halves, bears an uncanny resemblance to a reality hidden beneath the ice. Modern seismic surveys reveal that Antarctica is essentially two distinct landmasses. East Antarctica is a single, massive continental shield, while West Antarctica is a collection of smaller landmasses and islands, all buried under the ice sheet. Separating them is a deep subglacial channel. If the ice were removed, this channel would connect the Ross Sea and the Weddell Sea, creating a waterway that nearly splits the continent in two, just as Buache's map suggests. How could an 18th century theorist, working from symmetry and guesswork, land on a configuration that so closely matches a geographical truth that would remain hidden for over 2 centuries? To understand this, we must place Buache in his time. He was operating at the very edge of the known world. Empirical, survey-based cartography was becoming the standard, led by naval powers like Britain and France, who were sending ships to chart coastlines with increasing precision. Buache's method was almost the opposite. He was working from the inside out, using philosophy to shape geography rather than observation. An illustrative contrast makes this clear. Just a few decades after Buache published his theoretical map, Captain James Cook embarked on his famed voyages. He pushed further south than any European before him, eventually crossing the Antarctic Circle. What he found was not a temperate land with rivers, but a terrifying, impenetrable wall of ice. His maps recorded the edge of the ice shelf, the limit of what a ship could see and reach. They were masterpieces of empirical observation, but they told nothing of the continent's true shape beneath that frozen barrier. Buache's map, for all its theoretical origins, seems to hint at that hidden shape. This raises a fascinating possibility. Was Philippe Buache simply a brilliant guesser, or was his theory subtly guided by fragments of older knowledge? Historians note that Buache had access to the archives of the French Academy of Sciences, which housed accounts from earlier explorers and copies of ancient charts. It is possible that his mind, trained to look for patterns, subconsciously incorporated echoes from those older sources, perhaps whispers of a channel or a division that appeared in maps now lost. His symmetrical theory may have provided the perfect intellectual framework to rationalize and give form to these lingering, half-forgotten details. His map, therefore, represents a unique intersection. It is a product of Enlightenment rationality, yet it may also be the last, faint echo of that ancient geographical tradition, filtered through the lens of 18th century science. He did not claim to be copying an antique source, but his lines, drawn in the quiet of his study, accidentally traced the ghost of a continent that no one in his age could truly see. The year 1957 delivered a bombshell to the world of historical discovery. A previously unknown map surfaced, its simple lines depicting a startling addition to the medieval world. Alongside Europe, Africa, and Asia, it showed a large island in the Western Atlantic, labeled in Latin Vinlandia Insula. This was the Vinland Map, and it appeared to be a 15th century document confirming the Norse voyages to North America centuries before Columbus. The excitement was immediate and profound. Here, it seemed, was tangible cartographic proof of a pre-Columbian transatlantic crossing, a smoking gun drawn on ancient parchment. The map became a celebrity artifact, a symbol of rewritten history. Yet this celebrity status would soon plunge it into the center of one of the most bitter and enduring authenticity debates of the 20th century. The controversy turned on a single, microscopic clue. When scientists subjected the map to forensic analysis, they made a shocking discovery. The ink used to draw its coastlines contained a compound called anatase, a specific, industrially refined form of titanium dioxide. This substance was not commercially produced until the 1920s. The conclusion seemed inescapable. The ink was modern, therefore the map was a clever, modern forgery. The narrative flipped overnight. The celebrated window to the past was now seen as a mirror, reflecting the desires of the modern era to find validation for a cherished historical story. The case was considered closed by many, a lesson in how easily we can be deceived by what we wish to be true. But the story of the Vinland map is far more complex than a simple forgery tale. For every point that condemns it, a puzzling counterpoint emerges, creating a maddening loop of evidence. Start with the parchment itself. Radiocarbon dating has consistently placed the animal skin on which the map is drawn squarely in the 15th century. The vellum is genuinely medieval, so we are asked to believe a forger in the mid-1900s somehow acquired a blank, 500-year-old piece of parchment to use for his deception. This is unusual, but not impossible for a determined and well-connected hoaxer. The geographical content adds another layer of mystery. The depiction of Greenland on the Vinland map is remarkably accurate for its purported time, showing a detailed, jagged coastline that European cartographers generally got wrong for centuries afterward. Even more intriguing is the representation of Vinland itself. It shows a large island with two deep inlets, a configuration some researchers have compared to the Gulf of St. Lawrence and the estuary of the St. Lawrence River, areas we know the Norse explored. The critical question becomes, how would a forger in the 1950s have known to draw Greenland with such specific, correct detail? The scholarly work that pieced together the true shape of Greenland from Norse sagas and modern surveys was not widely synthesized and published until after the map had already appeared. If it is a forgery, it implies a forger with an exceptionally deep, almost prescient understanding of niche historical geography. Then there is the matter of the Anatase. While it is a hallmark of 20th century pigment, some scientists have cautiously noted that Anatase can occur naturally as a trace mineral. Could tiny, natural Anatase crystals have been present in the iron gall ink ingredients, perhaps from a particular sand or mineral used in its production? Other experiments have suggested that certain medieval ink recipes, when they degrade over centuries, can under specific conditions produce microscopic titanium compounds. The scientific debate is highly technical and remains unresolved, with each side accusing the other of methodological flaws. The provenance of the map is its own shadowy saga, a trail leading through rare book dealers and private collections that obscures its origins. This tangled history makes it difficult to establish a clear, unbroken chain of custody back to the 15th century, which fuels suspicion. Yet, the absence of a clear provenance is not proof of forgery, it is merely an absence. The Vinland map stands as the ultimate cautionary tale and an enduring riddle. It reminds us that the desire to prove a historical truth can sometimes blind us, and that modern science, while powerful, can also become a battlefield of interpretation. This map may indeed be a brilliant, cynical fabrication, or it could be a genuine medieval document that was, at some point, traced over or tampered with using modern ink, corrupting its evidence. Its legacy is a lesson in humility, showing that the line between a revolutionary discovery and an elaborate deception can be vanishingly thin, and that sometimes the evidence refuses to settle into a simple, satisfying story. While the Atlantic charts provoke mysteries, a parallel tradition of astonishing accuracy was flourishing in the East. The treasure ships of Admiral Zheng He were not vessels of exploration in the European sense, but floating embassies of staggering scale. Decades before Columbus crossed the Atlantic, these Chinese fleets, some containing hundreds of ships, were navigating the complex currents and monsoons of the Indian Ocean with a routine confidence that speaks to profound geographical knowledge. Their voyages were built upon a cartographic tradition that was both ancient and meticulously systematic, operating largely independent of the developments in the Mediterranean or the Atlantic. This was a world of grid-based maps and compass sailing, where accuracy was not a mystery, but a documented administrative achievement. In 1402, Korean cartographers synthesized this knowledge into a single magnificent work known as the Kangnido Map. This map presents a view of the world centered on China, but its scope is vast. It depicts the entire sweep of Afro-Eurasia, from Korea and Japan in the east to a broadly recognizable Europe and a surprisingly detailed Africa in the west. The Arabian Peninsula, the Indian subcontinent, and the Mediterranean Sea are all rendered in their approximate positions, a synthesis of Chinese, Islamic, and likely some filtered European geographical data. The Kangnido does not show the Americas, as its sources predated that contact, but its expansive, integrated vision of the known Old World stands as a testament to the sophisticated exchange of knowledge across the Silk Road and Indian Ocean trade routes. It proves that high-level global cartography was not a European monopoly. The source of much of China's maritime data was the treasure fleet itself. Admiral Zheng, his expeditions were not voyages into the unknown. They were state-sponsored missions of diplomacy and trade following established nautical highways. Their success relied on precision. Chinese navigators used detailed sailing directions or rutters, which recorded compass bearings between ports, notes on water depth, landmarks, and anchorages. They employed the magnetic compass, a Chinese invention, not just for direction but for measured course plotting. Their charts were often drawn on a grid, a practice that imposed a sense of scale and relative position, moving beyond mere pictorial representation. We can see the tangible results of this system in a later document, the Mao Kun Map. This chart, included in a 17th century military treatise, is explicitly based on the logs and charts from Zheng, his voyages over 2 centuries earlier. It maps the coastlines of Southeast Asia from southern China through the Strait of Malacca and into the Indian Ocean with a practical navigational clarity. The shapes of Vietnam, Thailand, and the Malay Peninsula are instantly recognizable, with bays, islands, and river mouths carefully noted. This is not an anomalous artifact hinting at lost knowledge. It is a surviving piece of a well-documented mapping methodology. It shows exactly what was possible within a known historical framework: systematic observation, careful record-keeping, and the institutional support of a powerful state. This documented Chinese precedent becomes a crucial counterpoint in the larger mystery. It demonstrates that ancient and medieval cultures were fully capable of producing remarkably accurate charts for the regions they regularly traveled. The precision of the Portolan charts in the Mediterranean finds its echo in the precision of the Mao Kun map in the South China Sea. Both were born from practical need, repeated voyages, and cumulative log-keeping. This established capability makes the extreme anomalies on the other side of the world even more puzzling. If Chinese techniques could accurately map the coasts they visited, and if Mediterranean techniques could accurately map their own sea, then the sudden appearance of a correctly charted Antarctica or a pre-Columbian America on a European map demands an explanation that goes beyond mere technical skill. It suggests a source. This is where the narrative takes a controversial turn. Some authors, most prominently Gavin Menzies, have proposed a radical theory that Zheng his fleets did not stop at Africa, but circumnavigated the globe, reaching the Americas and even Antarctica, and that their knowledge later filtered back to Europe to inspire the voyages of Columbus and the maps of Piri Reis. Mainstream historians and cartographic scholars almost universally reject this theory due to a profound lack of evidence. No Chinese maps from the period show the Americas. No archaeological traces of such a vast fleet have been found in the New World, and the official Ming records, which meticulously detail the voyages, contain no mention of such a monumental discovery. The strength of the Chinese example lies not in unproven global circumnavigation, but in its demonstration of achievable, localized accuracy. It provides a solid benchmark. We know what a map based on extensive first-hand naval reconnaissance looks like. The Mao Kun map is one. When we then look at a map like that of Piri Reis or Oronce Finé, we are forced to ask a different question. If the Chinese, with all their resources, did not map a continent on the other side of the Pacific, then who provided the data for the Turkish admiral's chart? The Chinese precedent does not solve the Western mysteries, it refines them. It shows us what is possible through documented exploration, thereby highlighting the features on other maps that seem to require a source of knowledge even more ancient or more obscure than the great treasure fleets of the Ming dynasty. A flat sheet of parchment holds a secret that only geometry can reveal. Every map ever drawn faces an impossible task: to take the skin of a sphere and flatten it without tearing the truth. This is the puzzle of projection, and it is here, in the warping of lines and the stretching of coastlines, that ancient maps whisper their most technical secrets. When a cartographer draws a continent, the method they use to translate the curve of the Earth onto a plane leaves a distinct fingerprint. Modern maps use mathematically precise systems, like the Mercator projection, which stretches the poles to preserve straight sailing lines, or the Robinson projection, which sacrifices some accuracy for a more pleasing, balanced look. These are conscious choices based on a sophisticated understanding of the planet as a globe. Early medieval world maps, the Mappimundi, showed no such understanding. They were often symbolic diagrams placing Jerusalem at the center within a circle of ocean, concerned more with theology than geography. The Portolan charts, by stark contrast, present a different kind of puzzle. They are not constructed on any known global projection like Mercator's, yet their coastlines are too accurate to be simple freehand sketches. Cartometric researchers, using specialized software, have attempted to digitally stretch these old charts onto modern projections to see what fits. The results are provocative. Some analyses suggest the Portolans align with startling fidelity when treated as a plain chart projection centered on a specific point in the eastern Mediterranean, such as the island of Rhodes or the city of Alexandria. Imagine a geometric process. If you were to take a large, flat sheet and place it tangent to a globe at, say, Rhodes, you could project the surrounding coastlines outward onto that sheet using straight sightlines. This creates an azimuthal projection, accurate near the center but increasingly distorted toward the edges. The dense web of Rhumb lines on a Portolan chart radiates from multiple points, creating a navigational grid that works remarkably well within the Mediterranean basin, as if the entire sea was mapped from a single, central vantage point of geometric knowledge. This leads to a crucial distinction. There is a profound difference between a map compiled from accumulated sailing directions and one constructed from a geometric model of the Earth. The first is a collage of local observations, a collection of coastal strips patched together. You would expect inconsistencies where these strips meet, slight rotations or scale changes, like assembling a puzzle without the picture on the box. The second is a unified creation, born from the idea that the world is a measurable sphere, and its parts can be placed in correct relation to one another through calculation. The Portolan charts show a consistency that hints at the latter. They do not look like collages, they look like integrated wholes. Consider a simple analogy. If you ask 10 people to each draw a detailed sketch of one room in a vast, unfamiliar palace, and then you tape those sketches together, the final floor plan will likely be a jumbled mess. Doors will not line up, corridors will bend at strange angles. But if one person uses a long measuring tape and a compass to survey the entire palace from a central hall, the resulting plan, while perhaps not perfectly scaled, will be coherent. The rooms will connect correctly. The Portolan charts feel like the work of that single surveyor with a measuring tape, not 10 different artists in 10 different rooms. This geometric coherence is what makes the larger anomalies so compelling. Let us apply this lens to a segment of the Piri Reis map, focusing on the coast of Brazil and that cryptic Antarctic tip. Some researchers have tested a theory that its source map was constructed using an azimuthal equidistant projection centered on a point in ancient Egypt like Cairo. This projection shows all points at their correct relative direction and distance from the center, but distorts shapes severely at the edges. When they digitally adjust the Piri Reis coastline according to this model, a fascinating thing happens. Certain alignments with the true geography of South America improve. The fit is not perfect, and the map fragment is too small for definitive proof, but the exercise is revealing. It suggests the original cartographer was not just copying shapes, he was copying shapes that had already been mathematically transformed from a spherical view to a flat one. They possessed not just the image of the coast, but the geometric framework that placed it on the globe. The absence of obvious conical or cylindrical projections in these old maps is in itself a clue. It tells us their makers were likely not thinking in terms of a global grid of latitude and longitude as we do. Instead, they may have been thinking in terms of direct, measured distances and bearings from a pivotal cultural or scientific center, a methodology that could yield stunning local accuracy and, if applied to a wider network of such centers, a surprisingly complete world picture. This technical analysis moves us beyond mystery and into the realm of capability. It suggests the builders of these source maps understood spherical geometry well enough to create a practical, navigable representation of their world. They may have solved the flat sheet problem not with our modern equations, but with their own elegant system of sightlines and measured arcs, a system so effective that its final products, copied and recopied for centuries, still challenge our assumptions about the past. A sea serpent coils in the Atlantic, its body a decorative border between the known and the unknown. These margins of ancient maps are a menagerie of imagination, filled with dog-headed men, cannibals feasting on shorelines, and the elusive, glittering kingdom of Prester John, a Christian empire rumored to be hidden deep within Asia or Africa. To the modern eye, these illustrations seem to discredit the entire document, reducing it to a work of fantasy. But this is a critical misunderstanding of the medieval and Renaissance mind. For the cartographers of these eras, their task was not merely to chart coastlines, it was to compile a complete encyclopedia of the world's knowledge, weaving together hard-won navigational data with the theological, historical, and legendary accounts that formed their cultural reality. The presence of a monster in the Southern Ocean does not mean the mapmaker doubted the shape of Italy. It simply means he was painting a fuller, more complex picture of creation as he understood it. Cultural historians note that these mythical elements served multiple purposes. They were warnings for sailors, filling terrifying blank spaces with understood dangers. They were expressions of wonder about the diversity of life, and often they were placeholders for genuine mysteries, a way of saying, beyond this point we have only stories. This is why our task is not to dismiss a map because it contains a dragon, but to learn how to read it with a critical, discerning eye. We must develop a framework to separate the likely factual data from the mythological overlay. The first filter is consistency. Look at the island of Brazil, a persistent phantom that appeared on Atlantic charts for centuries, often shown as a circular island west of Ireland. Its shape and location varied wildly from map to map, a clear sign it was based on rumor, not reliable survey. Now contrast that with the depiction of Ireland on the very same charts. While not perfectly scaled, its distinctive profile with the deep bite of Galway Bay and the southwestern peninsulas is remarkably consistent across dozens of Portolan charts. This consistency across independent sources points to a bedrock of verified observation. The second filter is correlation with physically verifiable features. Consider the treatment of Africa. A map might show the region south of the Sahara populated with the monstrous races described by the Roman writer Pliny, creatures with one giant foot or faces in their chests. Yet on that same map, the Mediterranean coastline of Africa, from the Strait of Gibraltar to the Nile Delta, could be drawn with the meticulous accuracy of a Portolan chart, because that coast was regularly sailed and surveyed. The mapmaker is not confusing fact and fiction. He is presenting both layers of his information side by side, one from direct experience, the other from inherited texts. The third and perhaps most important filter is the map's intended purpose. Compare two maps from the same 15th century workshop. One is a vellum Portolan chart, its surface a dense, practical web of Rhumb lines connecting accurately drawn ports, devoid of decoration except for precise city flags. Its purpose is survival at sea. The other is a lavish mappa mundi on parchment, meant for a prince's library, showing Jerusalem at the center, the Garden of Eden in the east, and the realms of Alexander the Great. This map is a statement of faith, power, and classical learning, its purpose symbolic, not navigational. The first prioritizes empirical data, the second prioritizes narrative and ideology. Applying this critical lens is our essential tool. It allows us to look at a chart like the Piri Reis map and understand its different layers. The sea monsters near Brazil are part of a common decorative tradition. The detailed rendering of the Andes Mountains, however, is an anomaly that demands a different kind of source. By learning to separate the serpent from the shoreline, we stop seeing these documents as either perfectly true or completely false. We begin to see them as complex historical artifacts, where a single stroke of ink might be a sailor's careful bearing, and the next might be a 1,000-year-old legend. This discernment is what allows the true, inexplicable anomalies to shine through the fog of myth, revealing the geographic truths that have no business being there at all. The flames that consumed the Library of Alexandria did more than burn scrolls. They severed a vital link in the chain of human memory. This legendary institution stands as the most compelling historical metaphor for the source of our anomalous maps, a central repository where the world's knowledge was once gathered, studied, and copied. It was not merely a storage room for books, it was the intellectual engine of the Hellenistic world, actively collecting works from Greek, Egyptian, Babylonian, and Phoenician scholars. As classicists note, its holdings certainly included the groundbreaking works of Eratosthenes, who calculated the Earth's size, and Marinus of Tyre, a geographer who attempted to map the entire known world using coordinates. This was a place where mathematical geography was a serious science. The hypothesis is elegant and haunting. Imagine that original survey maps, drawn from Phoenician voyages around Africa or from Alexandrian expeditions down the Red Sea, were deposited in the library's archives. These were not simple sketches, but the refined products of a scientific tradition that understood the Earth as a measurable sphere. For centuries, scholars would have consulted and copied these master charts, preserving their core geographical truths through generations of scribes. The theory proposes a tangible chain of transmission, a lifeline for data across millennia. After the library's long decline and eventual loss, its scattered contents did not simply vanish. Many surviving texts, including the geographical work of Claudius Ptolemy, found their way eastward to new centers of learning. Ptolemy's own writings, which became the foundation of medieval European cartography, explicitly reference and build upon the work of Marinus of Tyre and others, proving he had access to that older Alexandrian tradition. His maps, while influential, also introduced errors that distorted the ancient knowledge he was trying to preserve. From Alexandria, the stream of knowledge likely flowed to the great Islamic intellectual houses, like the House of Wisdom in Baghdad. Here, scholars translated and expanded upon Greek and Roman geographical texts, blending them with new data from Arab traders sailing the Indian Ocean. This fused body of knowledge would later travel west again, entering medieval Europe through centers of translation in places like Sicily and Toledo. It could have reached the port cities of Genoa and Venice, where practical chart makers might have incorporated fragments of this ancient world picture into their Portolan charts. To make this path concrete, consider an illustrative scenario. A Greek geographer working in Alexandria around 200 years before the Common Era compiles a world map based on a Phoenician captain's log detailing a circumnavigation of Africa. This chart, showing the continent's true shape, is copied onto papyrus and stored. Centuries later, a scholar in Baghdad, translating a damaged copy of that Greek text, carefully redraws the African coastline onto parchment, though he misinterprets some notes about southern landmarks. This Islamic chart eventually makes its way to a Catalan mapmaker in the 1400s, who integrates its outline of Africa into a new world map, now adding decorative kings and elephants where the original had only sailing directions. The original truth, the shape of the coast, persists through each copy, even as context and clarity fade. This library hypothesis provides a historical pipeline, a plausible, documentable route for lost data to travel from antiquity to the Renaissance. It does not require a lost super-civilization, only the acknowledged brilliance of ancient scholars and the tragic fragility of their records. It turns the mysterious maps into survivors, the last echoes of a grand conversation about the world that was happening long before we thought it possible. Across the globe from those parchment charts, another kind of map was being etched into memory under a vast, star-filled sky. The Polynesian voyagers who settled the Pacific Ocean represent perhaps the most stunning feat of human navigation in history. Their world was not drawn on vellum, but held in the mind, a living library of environmental knowledge that allowed them to cross thousands of miles of open ocean to find specks of land no larger than a dot. They are the ultimate counterpoint to our mystery, a known ancient culture that achieved the impossible without the tools we assume are necessary, proving that the human mind can become a perfect chart. Their story begins with scale. The Polynesian Triangle, defined by Hawaii in the north, New Zealand in the southwest, and Easter Island in the southeast, encompasses an area of ocean larger than all the continents combined. Within this watery expanse, they discovered and settled hundreds of islands, from the towering volcanic peaks of Tahiti to the low coral atolls of the Tuamatas. They did this without magnetic compasses, without sextants, and without any written maps as Europeans understood them. Their vessel was the double-hulled canoe, or waikolua, a masterpiece of maritime engineering capable of sailing against the wind. Their instrument was a profound, generational literacy in the language of the natural world. Modern wayfinders like Nainoa Thompson of the Polynesian Voyaging Society, who helped revive these arts, describe a system of mental cartography built on 3 pillars. The first is the star compass. Polynesian navigators memorized the rising and setting points of over 200 stars, creating a mental dome of the night sky. Each star was a beacon marking a specific direction from their home island. As they sailed, they would track their course by which stars passed over a particular point on the canoe, maintaining their bearing long after the island had vanished below the horizon. The second pillar is the reading of the sea itself. Master navigators learned to feel the ocean's swells, the deep, rhythmic pulses generated by distant weather systems and reflected by islands. An experienced wayfinder lying in the canoe could sense the subtle deflection and bounce of these swells as they interacted with an unseen island dozens of miles away, using the water's motion as a kind of sonar. They watch the patterns of clouds, which often gather and take on a greenish tint over the lagoons of low-lying atolls. The third pillar is the observation of life. Certain birds, like the white tern, are reliable indicators. These birds fish at sea but must return to land each night. By observing their flight direction at dusk, a navigator could find an island beyond the visible horizon. The drift of debris, the color of the water, and even the types of marine life present all became data points in a constantly updating mental model. Let us follow a hypothetical voyage from Tahiti to the Marquesas, a journey of roughly 800 miles northeast. The navigator, having memorized the star path, knows to keep the setting point of the star Arcturus directly astern. He feels the dominant easterly swell against the hull, using it as a steady reference. After 2 days, he notices a change in the swell pattern, a slight interference suggesting land to the north, perhaps the atoll of Rangiroa, though it remains unseen. He adjusts slightly, holding his course. Days later, the appearance of certain seabirds in the afternoon confirms he is on the correct approach. Finally, a specific cloud formation, stationary on the horizon, reveals the high peaks of Nuku Hiva. He has not followed a line on a chart. He has followed a songline written in the stars, the waves, and the wings of birds. This oral and sensory tradition is a form of data transmission as robust as any library. It was preserved through chants, stories, and rigorous apprenticeships that could last decades. The knowledge was not owned by one person, but held collectively, a cultural operating system for exploring a planet that is mostly water. The Polynesian example is transformative for our larger puzzle. It demonstrates conclusively that a pre-literate, ancient culture could build and maintain an exquisitely accurate model of vast geographic space. Their mental maps were not vague notions. They were precise, repeatable, and testable, allowing for intentional round-trip voyages across oceanic distances that would daunt modern sailors with all their technology. This forces a crucial reframing of the Atlantic and Antarctic mysteries. If the Polynesians could encode the Pacific in memory and tradition, is it not plausible that other seafaring cultures, now lost to time, developed similarly sophisticated systems for other oceans? Perhaps the source surveys behind the Piri Reis map were not drawn on papyrus at all, but existed for generations as an oral sailing lore of the Mediterranean or the Atlantic, a lore that was only later transcribed onto parchment by a scholar like the Ottoman admiral, who added the decorative monsters of his own time to a framework of much older, hard-won truth. The silent charts we study may be the fossilized remains of a wayfinding song that no one remembers how to sing. Gerardus Mercator's workshop in 1569 was a place of mathematical obsession. His goal was not just to draw the world, but to solve a practical problem for every sailor who would ever trust a chart. He devised a projection that transformed the curved surface of the Earth into a grid of straight lines, a lattice of latitude and longitude where a constant compass bearing could be drawn as a simple, unbroken stroke. This revolutionary tool, the Mercator projection, became the standard for navigation for centuries, but a quiet question lingers in the lines of his map. Where did the shapes of the continents he placed upon that grid actually come from? The 16th century was an age of explosive new geographical data, with ships returning from Africa, Asia, and the Americas. Yet the sudden, dramatic improvement in world maps during this period may have a second, less celebrated source: the rediscovery and incorporation of ancient data. Mercator himself provides a clue. In his writings, he openly credits classical authorities like Ptolemy, whose work had been rediscovered in Europe a century earlier. But he also makes cryptic references to what he calls other charts and plans of various origin, sources he does not name. This admission opens a fascinating possibility. Could the famed cartographer have been piecing together his modern world picture using fragments of much older surveys, templates that preserved geographical truths from a forgotten age? To test this, researchers sometimes perform a kind of cartographic archaeology, comparing coastlines across different eras. They look not just for accuracy, but for shared peculiarities. An error that appears on an older, mysterious chart and then recurs on a later, more scientific map can be a telltale sign of copying, a ghost in the machine of geographical progress. Take the enduring puzzle of Greenland. On the Zeno map from the late 1400s, it appears as a rugged, detailed island. On Mercator's own world map, Greenland is rendered with a similar, distinctive shape, particularly along its eastern coast. Yet when European explorers actually began to chart Greenland in detail in the 17th and 18th centuries, they found its outline to be far more complex and irregular. The curious thing is that the earlier pre-exploration maps, like Zeno's and even Mercator's, sometimes show a coastline that aligns more closely with what we now understand to be the true bedrock shape beneath the ice, rather than the jagged edge of the glaciers visible from a ship. This suggests these maps were not based on contemporary sightings, but on a common, older source that depicted the land itself, not its icy shroud. A compelling example of this slow data transfer can be seen in the north. In the 1420s, a Danish cartographer named Claudius Clavus created one of the first maps to incorporate Norse knowledge of the North Atlantic. His depiction of Greenland and the Nordic lands is crude but groundbreaking. If you overlay Clavus' simple outlines with the more refined versions drawn by later cartographers, including Mercator, you can trace a lineage. Each successive map adds detail, corrects some distortions, but retains a core geographical skeleton, the positions of key promontories, the general orientation of the landmass. This looks like a continuous tradition of improvement, a slow filtering of ancient Norse sailing knowledge, preserved in local sagas and perhaps in lost logs, into the mainstream of European cartography. Mercator, a meticulous scholar, would have sought out every available source. It is entirely plausible that he obtained copies of charts derived from Norse voyages, or even fragments of the Portolan tradition, and integrated their coastal data into his grand mathematical framework. His genius was not necessarily in discovering new shapes, but in placing old, reliable shapes onto a projection that made the entire world navigable. This connection reframes the map-making revolution. It was not a sudden leap from ignorance to knowledge, but a merging of streams. One stream was the fresh, first-hand accounts from Portuguese caravels and Spanish galleons. The other, deeper and older, was a trickle of preserved data from antiquity, flowing through libraries, Islamic scholars, monastic scriptoria, and the hands of practical chart makers. Mercator stood at the confluence. His map, therefore, is a palimpsest. On its surface are the straight Rhumb lines of a new navigational age. Beneath those lines, if we look closely, we might just discern the faint, stubborn coastlines from a world much older than his own, preserved not by accident, but by their enduring, inexplicable accuracy. The captain's memory was a living chart, a constellation of landmarks, wave patterns, and star paths held in his mind. For generations, this was how the sea was known, through stories chanted on night watches and skills passed from elder to apprentice. Then, in a quiet scriptorium overlooking a bustling Mediterranean port, a profound shift occurred. A master mariner sat with a skilled draftsman, not to tell a story, but to build a picture. He began to describe, headland by headland, the shape of the world as he knew it from the deck of his ship. This was the moment of translation, when fluid, experiential knowledge was frozen into the fixed lines of a Portolan chart. Cognitive scientists who study spatial reasoning note this is a complex transformation. The mind does not store geography like a photograph. It holds relationships, sequences of events, and sensory cues. A sailor knows that after 2 days sailing with the north wind, a distinctive red cliff appears, and that a certain current near that cliff means fresh water is near. Translating this into a static, scaled drawing required abstracting those lived experiences into angles and distances. The draftsman's tool was the wind rose, a circle marked with the directions of the winds. From this, they built a scale. The captain would say the journey from Marseille to Genoa took a day with a favorable wind. The draftsman, using a standard day's sail distance for that type of ship, would plot the corresponding length on the vellum, aligned with the correct Rhumb line radiating from the rose. This process, repeated for hundreds of segments of coast, slowly assembled the map. It was an aggregation of practical knowledge, a consensus of countless voyages suddenly made visible and shareable. Yet this act of preservation was also an invitation for error. The potential for corruption began the moment the first line was copied. A tired scribe might misplace an island by a fraction of an inch on the parchment, an error that on the open sea could mean miles. Different captains might estimate the same sailing time differently, leading to charts of varying scales that were later combined, subtly stretching or compressing coastlines. Some masters protective of lucrative trade routes might intentionally omit a safe harbor or add a phantom reef to mislead competitors, turning a tool of truth into one of deception. We can watch this process unfold by tracing a single coastline across time. Take the rugged coast of Brittany in France. On a Portolan chart from the late 1300s, its jagged profile, with the deep indentation of the Bay of Biscay and the protruding peninsula of Finisterre, is already remarkably recognizable. A chart from 50 years later shows the same shape, but perhaps with a small, sheltered bay drawn slightly more to the east. Another 50 years on, that bay might have migrated further, or a tiny island might have appeared offshore that does not exist. The core truth of Brittany's outline remains stubbornly consistent, a testament to the accuracy of the original oral surveys. Yet the details drift like sand, showing how noise enters the signal over generations of copying. This procedural view resolves a paradox. It explains both the stunning accuracy of the Portolan charts, born from centuries of accumulated sailor wisdom, and the strange anomalies that later puzzle historians. A feature that seems like an impossible premonition might be the preserved echo of a real but forgotten voyage. A glaring error might be the accumulated distortion of a dozen copyists' hands. The chart is not a snapshot of a single truth, but a parchment palimpsest, its lines recording not just geography, but the very history of how knowledge was passed down and how fragile that transmission could be. The world's coastlines were not revealed in a single age by a single, forgotten race. They were pieced together slowly over countless generations by people whose names are lost to the sea. This is the quiet, cumulative story of human curiosity, a narrative that orthodox archaeology finds written not in grand ruins, but in scattered seeds, shared words, and the silent testimony of artifacts far from home. Historian Felipe Fernandez Armesto reminds us that the pre-modern world was far more dynamic and interconnected than we often assume. A place of constant, small-scale exploration by fishermen following the shoals, traders chasing the monsoon winds, and adventurers simply wondering what lay beyond the horizon. Each of these journeys, however brief or accidental, added a tiny fragment to the collective understanding of the world. A Norse Nar, blown west from Greenland, might have glimpsed the forested shores of Labrador. A Malay trading vessel riding the Indian Ocean currents could have been swept south to the lonely beaches of Madagascar. These were not state-sponsored missions of discovery, but episodes of survival and happenstance, their stories told around hearths and in harbors, slowly weaving a tapestry of geographical rumor that was, in its essence, surprisingly accurate. The evidence for this incremental model is circumstantial but compelling, built from a mosaic of clues that mainstream scholarship continues to assemble. Consider the spread of biological and cultural materials. The sweet potato, a plant native to South America, was found across Polynesia long before European contact. The bottle gourd of African origin appears in ancient American archaeological sites. These are not proofs of direct, organized contact, but they are strong indicators of transoceanic drift, of voyages that carried more than just stories. Linguistic ties hint at ancient connections, like the Austronesian roots in the language of Madagascar, an island off the coast of Africa, suggesting a migration from Southeast Asia thousands of years ago. Then there are the artifacts that simply feel out of place. Roman coins occasionally surface in American soil, though most are later losses or modern introductions. A more tantalizing case might be a piece of pottery with a Mediterranean glaze found in a pre-Columbian layer, though such finds are hotly debated and often explained by later contamination. The point is not that any one piece of evidence is definitive, but that together they sketch a world where the oceans were less barriers and more highways for the bold and the unlucky. To make this concrete, let us follow a speculative but plausible voyage. In the 1st century, a Roman merchant ship, a sturdy vessel designed for the grain trade, is caught in a powerful Atlantic storm off the coast of West Africa. For weeks, it is driven westward by winds and currents it cannot fight. Finally, land appears, not the familiar dunes of Libya, but a lush, tropical coastline with vast rivers. The surviving crew, desperate for fresh water and food, explore the river mouth. They make notes of the stars, the sun's angle, the shape of the bays, perhaps sketching a crude chart on wax or simply committing it to memory. Eventually, they repair their ship and, catching the right winds, make the perilous journey back east, perhaps landing in the Canary Islands or even making it all the way back to a port in Mauritania. Their incredible tale is recorded in a captain's log, a periplus which finds its way to the great Library of Alexandria. There, a geographer like Marinus of Tyre incorporates this strange western land into his notes on the world's edges. Centuries later, a copy of that corrupted note is used by a Renaissance cartographer trying to make sense of new Portuguese reports from Brazil. The coastline on the final map is a blend of ancient accident and modern confirmation. This model requires no global cataclysm or advanced progenitor civilization. It only requires the relentless patchwork nature of human movement and the fragile, tenacious threads of how knowledge is passed down. It accepts that most of these voyages left no permanent colony, no enduring monument. They left only a story, a measurement, a single coastal profile that entered the stream of geographical lore, to be preserved, distorted, or forgotten, waiting for the day it would be copied onto parchment and puzzle the future. The evidence sits before us, but the real mystery may lie within our own minds. There is a profound and deeply human allure to the idea that our history is not what we were taught, that a more advanced or interconnected past has been erased, waiting to be rediscovered by a lone, insightful researcher. This psychological pull is a powerful force, one that shapes how we interpret every line on these ancient charts. At its core, this fascination challenges a subtle bias known as chronological snobbery, the unexamined assumption that people in the past were inherently less intelligent, less curious, or less capable than we are today. The notion that a Renaissance admiral or a medieval monk could possess knowledge that defies our timeline feels like an exhilarating correction to that bias. It suggests our ancestors were not primitive, but perhaps possessed different kinds of sophistication, different paths of knowledge that we have since forgotten. This taps into a cultural craving for a past filled with more wonder than our standardized histories often provide. Sociologists note that alternative historical narratives fulfill a powerful role in popular culture. They offer a compelling story structure, one with clear heroes and obstacles. The narrative often follows a familiar arc. A dedicated outsider, perhaps a professor like Charles Hapgood, uncovers a startling anomaly that challenges the textbook narrative. The academic establishment, portrayed as rigid and invested in the status quo, initially dismisses the find. This creates a classic underdog story where new evidence battles against entrenched dogma. For the public, this is far more dramatic and personally engaging than the slow, collaborative, and often uncertain grind of mainstream historical research. It transforms history from a settled fact into a living detective story where anyone, including the viewer, can participate in the puzzle. Consider the public reception of the Piri Reis map when it was rediscovered in the mid-20th century. It arrived at a time of growing fascination with lost continents like Atlantis and Mu, ideas popularized in pulp magazines and speculative books. The map was not just a curious artifact, it was a potential key, a tangible piece of evidence that could validate a grander, more romantic vision of human origins. It offered a what-if scenario of immense power. What if a great seafaring culture mapped the world before the ice came? What if our timeline is just a fragment of a much longer human story? These questions are not just about geography, they are about identity and meaning, offering a sense of mystery that orthodox history, with its emphasis on evidence-based gradualism, can sometimes lack. This allure exists on a spectrum, however, and it is crucial to differentiate between healthy skepticism and dogmatic belief on all sides. On one end, there is the open-minded researcher who says, "This anomaly does not fit our current model. Let us investigate it without prejudice." This is the spirit of genuine inquiry. On the other end, there can be a form of belief that dismisses all contradictory evidence as part of a cover-up, a mindset that finds the conspiracy more appealing than the complicated truth. Similarly, the orthodox response has its own spectrum. It ranges from rigorous, evidence-based skepticism, which is essential to the scientific process, to a kind of institutional inertia that can be too quick to dismiss anything that disrupts the consensus. The illustrative example of Atlantis is telling. For some, it is a philosophical metaphor for a lost golden age. For others, it is a literal continent to be found. The Piri Reis map for a time became a piece in that literal puzzle. Understanding this psychological landscape is not about dismissing the maps, but about refining our own perspective. It allows us to separate the emotional appeal of a rewritten past from the cold, geometric data on the parchment. It reminds us that we are not just evaluating ink and vellum. We are confronting our own desires for a world more mysterious and a history more profound than the one we think we know. This self-awareness becomes our most important tool as we move from the allure of the mystery to the final, daunting task of weighing all the evidence together. A quiet revolution in mapping began not with ships but with satellites. High above the Earth, instruments like the GeoSat and GRACE satellites measure the planet's gravity field with exquisite sensitivity. They do not photograph the ocean floor or peer through ice, they feel it. The subtle pull of a hidden underwater mountain or a deep subglacial trench creates a tiny variation in gravity, which these satellites detect. This data, processed by supercomputers, allows geophysicists to construct maps of the Earth's bedrock hidden beneath miles of water or ancient ice. For the first time in human history, we have a precise, global picture of the true shape of our planet, a definitive benchmark against which every ancient chart can be measured. This is not speculation, it is a mathematical portrait of the world unseen. Geophysicists like those at the British Antarctic Survey now work with these bedrock models daily. They are not searching for lost civilizations, they are studying climate change and tectonic history, yet their maps provide the ultimate test for the anomalous coastlines on parchment. The process of comparison is a meticulous science in itself. First, a digital version of an old map, like that of Oronce Finé, is georeferenced. This means key points on the old coastline are tentatively aligned with known points on the modern bedrock map. Because the old map's projection and scale are unknown, this is an iterative statistical process. The software stretches, rotates, and scales the old image, searching for the best possible fit across hundreds of coastal data points. The result is not a simple yes or no, but a correlation coefficient, a number that tells you how likely it is that the alignment is due to chance. For the Finé map, the results are provocative. When the old coastline is digitally adjusted, certain sectors show a correlation that is difficult to dismiss. The area corresponding to the Ross Sea sector, for instance, reveals a series of coastal indentations and promontories that align with the subglacial features we now know exist. The prominent peninsula on the Phineas map aligns with the modern Antarctic peninsula's orientation. The deep gulf he labeled matches the general position of the Weddell Sea's indentation. These are not perfect matches. The old map is distorted, as any copy of a copy would be, but the statistical relationship in these key areas suggests something more than random guesswork. It suggests a common source shape. The Buache map, with its theoretical division of Antarctica into two islands, presents a different kind of puzzle. Modern bedrock maps confirm that if the ice were removed, West Antarctica would indeed appear as a separate archipelago from the single massive shield of East Antarctica, with a deep seaway between them. Buache's Central Sea is in approximately the correct location. His error was in making the two landmasses too symmetrical and circular, a product of his philosophical method. Yet the core idea, a fundamental division, is eerily present in the data he could not possibly have accessed. This scientific grounding transforms the mystery. It moves us from wondering if an old map looks right to measuring how closely it aligns with verifiable truth. The process also highlights discrepancies which are just as important. Large sections of the Phineas map do not align well, showing where copyists may have guessed where the source data was poor or where the original map was simply wrong. This balanced view is crucial. It prevents us from seeing only what we want to see. Instead of a vague sense of wonder, we are left with a specific, data-driven anomaly, certain coastal segments on a 500-year-old document that resonate with a landscape hidden for millions of years. The satellites have given us the answer key, and now we must decide how the questions were written so long ago. The Haji Ahmed map of 1559 presents a world in graceful, swirling arcs. This Ottoman masterpiece is not a simple copy of European models. It arranges the continents in a fluid, almost artistic composition that feels both familiar and strangely alien. Its most discussed feature lies in the vast Pacific Ocean, where the western coast of the Americas is drawn with a peculiar and specific error. California is depicted as a large, vertical island, separated from the mainland by a narrow strait. This was a common cartographic myth of the era, but on Haji Ahmed's chart, it is rendered with an unusual level of internal detail, showing bays and coastal features that suggest more than mere guesswork. The map stands as a distinct enigma, a synthesis of Ottoman artistic sensibility, emerging European data, and whispers of something else entirely, perhaps source material focused on the Pacific Rim that has since been lost to history. Cartographic historians note the map's unique projection, which seems to compress the Atlantic while giving expansive, detailed treatment to the lands bordering the Pacific. This focus is intriguing. At a time when most European mapmakers were obsessed with the Atlantic and the route to the Indies, Haji Ahmed's work suggests a different geographic priority. It raises the possibility that he had access to reports or charts from a perspective that looked eastward across the Pacific, rather than westward across the Atlantic. Some researchers propose this could reflect filtered knowledge from across the Bering Strait, perhaps from indigenous trading networks that connected Asia and North America for millennia. Others point to the possibility of lost Spanish expeditions along the western coast of the Americas in the early 1500s, voyages whose records may have circulated in Mediterranean ports and been acquired by Ottoman scholars. To assess its value, we can zoom in on a specific area, its depiction of Northeast Asia. The map shows Japan labeled as Sipangu, and the Korean peninsula with a shape and orientation that is surprisingly advanced for its time. When compared to Portuguese charts from the same period, which were based on direct trade contact, Haji Ahmed's version holds its own. It captures the general relationship between Korea and Japan and the curve of the Asian coastline northward. This accuracy in a region where the Ottomans had no direct political reach suggests he was working from a composite of high-quality sources, not just rumor. It indicates he was part of a vibrant, international exchange of geographical knowledge, where a chart from a Portuguese caravel in Macau could, within a few decades, influence the work of a cartographer in Istanbul. The map of Haji Ahmed does not provide easy answers, but it adds a crucial, complex thread to our story. It demonstrates that the flow of cartographic data in the 16th century was not a one-way street from Europe outward. It was a multidirectional conversation, a noisy marketplace of ideas where Ottoman, European, and possibly much older traditions could be blended into a single, cohesive design. His depiction of California as an island is not proof of pre-Columbian Pacific voyages, but it is a fossilized era that contains within it a specific vision of that coastline, a vision that begs the question of its origin. In the elegant arcs of his map, we see the global puzzle taking shape, a reminder that every line drawn was a hypothesis about the world, tested not just by ships, but by the slow, patient work of scholars comparing charts across continents and centuries. The ink has dried, the coastlines are drawn, and the theories have been laid before us. After this journey across centuries of parchment and possibility, we find ourselves not with a single, triumphant answer, but with a table scattered with puzzle pieces from different boxes. The true challenge now is not choosing one grand story, but assembling a coherent picture from fragments that refuse to fit a single narrative. No single theory holds all the keys. The romantic vision of a single, globe-spanning lost civilization is a powerful narrative, but it demands evidence that remains, for now, buried deeper than the Antarctic bedrock. Conversely, dismissing every anomaly as forgery or coincidence ignores the stubborn, geometric truths that whisper from the vellum. The most honest perspective lies in the nuanced middle, a spectrum of likelihoods where human ingenuity and forgotten voyages intertwine. A historian of cartography looking at this collection would likely begin by separating the maps into distinct categories of mystery. The Portolan charts stand as masterpieces of practical, cumulative knowledge. Their sudden appearance speaks not of a single lost source, but of a brilliant, coordinated effort to synthesize centuries of Mediterranean sailing experience into a usable, geometric system. They are proof that ancient and medieval mariners were far more capable than we often credit, able to achieve stunning local accuracy through observation and shared tradition. Then we have the Piri Reis map, a fascinating collage. It is almost certainly a compilation, as the admiral himself claimed, blending contemporary Portuguese charts, classical legends, and most intriguingly, fragments of much older source material. The correlations of its Antarctic coastline are too specific to dismiss entirely, suggesting it preserves a ghostly echo of a geography from a different climatic age, copied and recopied until it reached his desk. The Vinland map, however, resides on the opposite end of the spectrum. The modern chemical signature in its ink is a formidable obstacle. While the debate over Anatase is technically complex, the simplest explanation is often the most probable. It is most likely a clever, mid-20th century creation that tapped into a deep cultural desire for pre-Columbian validation. Yet, even here, a sliver of doubt remains, not about the map itself, but about the precise origin of its remarkably accurate Greenland, a detail that hints at the forger's own deep and perhaps troubling research. The strongest evidence for some form of lost or overlooked ancient knowledge rests on three pillars. First are the Antarctica correlations, particularly on the Finé and Piri Reis maps, which align with subglacial features in a statistically significant way. Second is the unexplained sophistication of the earliest Portolan charts, which appear without clear precedent. The third is the persistent cross-cultural claims by the mapmakers themselves, from Piri Reis to Mercator, that they were consulting ancient sources. We can construct a most likely historical scenario that requires no cataclysms or super civilizations, only an expansion of our understanding of the past. Imagine a Bronze Age and classical world where exploration was more extensive, though poorly recorded. Phoenician vessels may have ventured farther down the African coast. Minoan traders could have mapped the Black Sea with a surveyor's eye. Norse sagas may have preserved true coastal profiles in poetic form. The knowledge from these voyages, perhaps held in the Library of Alexandria or other great centers, formed a corpus of advanced geography. This corpus was fragmented by the fall of empires, its pieces scattered. Some fragments survived in Islamic libraries, others in monastic scriptoria. Over centuries, these precious, corrupted copies sporadically resurfaced, influencing a Catalan chartmaker here, an Ottoman admiral there, and a Flemish genius like Mercator. The maps we puzzle over are not the original surveys, but the last, faint fingerprints of those surveys, smudged by time but still bearing a trace of their original shape. This measured view accepts mystery without requiring myth, and it leaves one final, forward-looking question hanging in the air. The search for these maps does not end in a dusty archive. It is a living investigation, propelled forward by technologies our ancestors could not have dreamed of. While we sift through the past, the future of this mystery is being written in lines of code and beams of invisible light. Imagine the sheer volume of historical material still untouched, the uncatalogued manuscripts in a remote monastery, the forgotten chest in an aristocratic attic, or the sealed jars in an archaeological storeroom. Any one of them could hold the next piece of the puzzle, a chart that reconnects a broken lineage or presents a wholly new anomaly. This is not just hopeful speculation. It is the daily work of a new generation of scholars armed with digital tools. Across the globe, digital humanities projects are undertaking monumental tasks. They are creating high-resolution scans of thousands of historical maps, building a global library of cartographic memory. But the real revolution lies in what comes next. Researchers are developing sophisticated algorithms, a form of artificial intelligence that can analyze these maps not as pictures, but as complex datasets. These programs can compare the precise curvature of 100 different depictions of the same coastline, searching for statistical patterns that reveal a common source. They can trace the migration of a specific era, like a misplaced island, across centuries and continents, mapping the family tree of copied knowledge. One of the most promising applications is the mathematical reversal of distortion. Think of an old map as a photograph that has been crumpled, stretched, and faded. New software can attempt to digitally smooth it out. By identifying known control points, like the location of a major city that has not moved, the algorithm can work backwards. It applies complex geometric transformations, testing different map projections until the chart's internal relationships snap into a coherent, geographically logical form. This process can, in theory, strip away the stylistic choices and copying errors of later draftsmen to reveal the raw geographic data points that informed the very first survey. The technologies enabling this are both delicate and powerful. Multispectral imaging uses different wavelengths of light, from ultraviolet to infrared, to see beneath the surface of a manuscript. It can reveal erased text, a palimpsest where a later map was drawn over an older one, or faint ink traces that have faded to invisibility. Improved methods of radiocarbon dating provide more precise ages for the parchment itself, helping to authenticate a document's material origins. And global databases are being built, cataloging every named place, every ship drawing, every compass rose, allowing for instantaneous comparisons across cultures and centuries. Let us envision a potential discovery born from this convergence. A scholar translating a neglected Byzantine manuscript in a digital library, encounters a passing reference to a chart of the Western Ocean that was consulted by the librarians of Alexandria. This footnote mentions it was copied for a Roman expedition. Armed with this clue, researchers could then scour global databases for any map fragment that matches a specific, archaic terminology for ocean currents described in the text. Simultaneously, multispectral imaging on a known but puzzling Portolan chart in Venice might reveal a fainter, older set of lines beneath the visible ink, lines that, when processed by an algorithm, resolve into a coastline that matches the Roman description of a distant western land. This is not science fiction, it is the emerging methodology of 21st century historical research. The potential finds are breathtaking. A previously unknown Portolan precursor could be discovered in an Egyptian tomb, preserved in the dry climate, showing the Mediterranean with a geometric precision that predates the known examples by 1,000 years. Deep within the Chinese imperial archives, a map commissioned by a Ming emperor might be found, not showing the Americas from Chinese voyages, but incorporating a complete world map acquired from Silk Road traders, a snapshot of global knowledge from a specific moment before the age of European exploration. Or, perhaps most provocatively, a verified pre-Columbian map of the Americas might surface, not drawn on parchment, but etched in stone or woven into a textile, depicting the continent from an indigenous perspective that records coastlines with a detail that stuns modern cartographers. The search for truth in these ancient lines is an ongoing journey, not a finished story. Each technological advance is a new lens through which to examine the past, offering not just answers but undoubtedly new and deeper questions. The mystery persists not as a failure of our understanding, but as an invitation to keep looking. Our journey across these vellum landscapes now draws to a close. From the cryptic lines of the Piri Reis fragment to the precise grids of the Portolan charts, from the theoretical Antarctica of Buache to the wayfinding genius of the Polynesians, we have navigated a sea of questions. The ultimate takeaway is not a single, definitive answer, but a profound appreciation for the gaps and glitches in our historical record. These maps are not just drawings, they are whispers from the past, faint echoes hinting at voyages forgotten, knowledge lost to the tides of time, and perhaps entire chapters of the human story that remain unremembered. They stand as a direct challenge to the quiet arrogance of assuming we know the full scope of ancient human curiosity and capability. Whether your own conclusion leans toward the orthodox explanation of slow, cumulative discovery across generations, or you find yourself drawn to the more radical theories of lost advanced cultures, these artifacts undeniably expand our sense of wonder. They stretch the timeline of exploration and force us to reconsider what our ancestors might have known. Let this exploration serve as a lasting reminder that the world's map, both physical and historical, is still being drawn, its coastlines refined with each new discovery and each reinterpretation of an old, puzzling line. If these mysteries have captivated you, the journey does not have to end here. Delve deeper by exploring the sources and further reading we have linked below. And we genuinely want to hear your own theories in the comments below this video. After following this trail of evidence, where do you land? Are these maps the fragmented legacy of a world lost to deep time? Or are they simply the remarkable, collective product of our endlessly ingenious ancestors, whose true achievements we are only now beginning to measure? Subscribe and join us as we continue to seek out and unravel history's greatest enigmas, one forgotten map